Hi everyone, we're the Engineering Chicks. I'm Ashley and I'm here with Emily, and today we're going to be going over the Monty Hall problem. So this problem, it actually started on a game show. So you'd have three doors, and behind each door was either a car or goats. So the car is only behind one door and the other two doors have goats. So the problem says that if you pick, say, door number one, you have a 1/3 chance of the car being behind that door. So that leaves a 2/3 chance of the car being behind the other two doors. So on the game show, you pick door number one, and then the host will reveal where one of the goats are behind one of the other two doors. So that leaves a 2/3 chance of the car being behind the last unopened door. So you can choose to either keep the door you picked or switch to the last unopened door. And statistically, you have a 2/3 chance of getting the car if you switch at the very end.
Okay, so going into our code and actually proving Monty Hall through Monte Carlo simulation, we've got our count of winning up here initialized at 0. We decided that door number 3 would be the door that has the prize, and you can kind of see that up here. We just laid that out for our own sakes of just knowing which is which. And then we're running this for 10,000 times, and then coming into our for loop, we've got a random number being generated. Of course, each door has the same probability of being chosen, so it's a 1/3 chance. And so if you go through our code, it's saying that we're going to count the winnings. So we're assuming that they swap every time. And if you assume that if they pick door number 1, the host will reveal door number 2 to them. So they know that one's obviously doesn't have the winning car in it. So we're assuming that they decide to swap every time. And if they swap, of course, they're going to choose door number 3, which has the car behind it, so they end up winning. And the same scenario for door number 2. If they pick door number 2, the host is going to reveal to them door number 1, and so they're going to swap. We assume that they always swap, and so they'll pick door number 3. Now, else being the remaining like 1/3 of our probability, if they choose that one initially, we don't count it up because obviously they wouldn't want to swap it. So here we'll go ahead and run the code, and as you can see, our probability of winning is around 2/3. So if you swap the doors and you win, you have a 2/3 chance of winning. And then of course the probability of winning if you don't swap would be 1 minus that, and so we got about 1/3, which mathematically lines up to the Monty Hall problem, and you can see that we've successfully proven Monty Hall using Monte Carlo simulation.